It's well known that gravity pulls two objects together with a force proportional to the mass of one times the mass of the other, divided by the square of the distance between them. This equation is called Newton's law of universal gravitation. It's taught to school children the world over, and it predicts the motions of the planets and moons and asteroids in our solar system with incredible precision. However, Newton's law of universal gravitation isn't actually a universal law. First, we know that when the gravitational force in question is really strong, Newton's law is just wrong. And second, we know that when the gravitational force in question is really weak, we don't know whether it's right or wrong because gravity gets too weak to measure. Only in between, like on the scale of the solar system, do we know that the law of gravitation reasonably applies. Okay, but if Newton's law of gravitation has been confirmed so accurately by the motions of planets and moons, how could it be wrong at a different scale? Well, the Earth looks flat when you're relatively close to the ground, but zoom out and it looks round. Or zoom in and it looks bumpy. The law describing the shape of the Earth is different at different scales. Similarly, when the force of gravity is really strong, like near a black hole, gravity is better described by the mathematics of general relativity, and only when the forces in question get a bit weaker, for things farther apart or with less mass, does gravity start to match up with Newton's law of gravitation. But when you go even weaker, with objects even farther away or even less massive, we get to a point where we don't know whether Newton's law of gravitation applies anymore. And yet even many physicists appear to be ignorant about our ignorance about how gravity works when it's weak. Or at least they ignore our ignorance. It's common to blindly apply negative GMM over r squared to decidedly non-astronomical objects, for which we haven't tested gravitational attraction very well at all. If you have two pieces of tape, you can calculate the gravitational force that they in principle exert on each other according to the law of universal gravitation, but it's far too ridiculously small for you to ever have the remotest chance of noticing any effect whatsoever, let alone actually checking that the attraction between them follows the law of universal gravitation as you move the bits of tape farther apart. In contrast, if you stick the two pieces of tape together and then pull them apart, they'll exchange some electric charge and then measurably attract each other, an electrical attraction which is 1,000,000 billion times stronger than the predicted gravitational attraction, and whose strength has allowed us to confirm Coulomb's law of electrical attraction to a very high degree of accuracy. So it makes sense to apply Coulomb's law of electrical attraction to objects at normal human scales. But testing Newton's law of gravitation at these scales requires very delicate experiments.